what VSEPR is valence, shell, electron pair repulsion theory. You need to know that definition for your test. I'm telling you a couple points of your test. I'm going to say, what is VSEPR? You've got to define it for me. So make sure you know that definition by next week. Valence, shell, electron pair, repulsion. And the key word, guys, right there, what do you think is the key word? Nope. Repulsion, guys. Repulsion is the key word. All right, this is a way to predict the molecular geometry. All molecular geometry means is the shape. What's the actual three-dimensional shape? And right here, guys, there's a repulsion between electrons. We know that. Electrons are negative. They want to repel each other. Again, like I said last week, you need to memorize the VSEPR table, guys, at the front page, or page 2 of your packet. All right, it's the top 6 rows. You don't need to worry about trigonal bipyramidal, and you don't need to worry about octahedral for that. Make sure you know the first 6. So, our process is going to be exactly the same. First thing we got to do is actually draw the structure out. Okay, like we've done. Once we've drawn the structure, then what we're going to do is we're going to put in ABE form. Now, for some of you guys, the formulas may work. For some of you, you may just be able to see it. That's fine, too. As long as you know what the shape is, I don't care how you get there, whether it's using the formula or just memorizing and recognizing the shape. Okay, it depends on how your mind works. For the formula, A represents the central atom always. B represents the bonded atoms to A. E represents lone pairs electrons on A. The big note to mention here, though, folks, is right here. Lone pairs are only in relation to... So when we're talking about lone pairs, it's only in relation to the central atom, not your satellite atoms. So when we start to count them, I see people make mistakes all the time because they start looking at all the dots instead of just the center ones. All right? Then once we have our formula, guys, then we will predict the shape. Again, by drawing it out, you may just start to, the more practice you do, recognize and see the shapes, and that's fine. You don't necessarily have to use the formula. The formula may be confusing to you if you don't like formulas. If you're not very analytical and you're more visual, the visual way will be better. Either way, as long as you get the correct shape. All right? And you'll want to know it, be aware of it for your quiz tomorrow. You may see it on there. So, first things first, we're going to draw our structure. So I want you guys to take the next couple minutes and draw the shape, predict the shape. Just draw the structure for CBr4 right now. So this should be our structure for carbon tetrabromide. Anything new yet? No, we've been doing this for a while. The new piece now, guys, comes with this step 2. We're going to put in ABE form. If you have a different color, I would encourage you to use it, whether it's a highlighter or use a colored pencil or a different color pen or whatever. If you don't have one, you don't have to use one. It's just I'm going to use one, so you may want to as well, to help see what we're going to do here. Now, once we have our structure, we're going to figure out or predict the shape, and based on the formula. So what I'm showing you guys is going to be the formula structure or way to figure it out. So A, we're going to put an A over the central atom. So I'm going to write an A right there over my center one. The shape is all based upon your central atom, guys. It's in relation to your centerpiece. Okay? It's not in relation to bromine or any of the satellite atoms. It's the center atom, what we're working on or what we're looking at. Then we're going to put letter B's next to any of the atoms that are bonded to A. Now, folks, notice here, B may be different elements. It does not have to be all the same one. It's any satellite atoms that you have attached to your central one. So all of these, this is going to be a B, B, and B. Now, the last one has E, represents any lone pairs of electrons on our central atom, which is A. In this example, do we have any lone pairs on A? No, so that's not going to be part of our formula. So now when we add everything up, guys, A, B, how many B's do we have? 4. So if you take a look here, A, B, Y, EZ, guys. Y and Z just are subscripts, and we know that subscripts represent the number of atoms or the number of lone pairs that we have, just as we've seen with any structure. So, our shape is going to be based on this formula of AB4. Well, if we take a look at that page in your reference, or in your note packet, okay, we're going to then look for the AB4 formula. Well, that's right here. What shape does that correspond to? Tetrahedral. So my shape here with CBr4 is tetrahedral. Now, going back to Josh's question earlier, where he said, can we write water as linear? You can for your first structure that you may have, but your final one, once you know the shape and the geometry, you have to redraw it to show what shape it is. Does that make sense? So your first initial one, guys, when you're just trying to figure out your basic structure, absolutely, draw it however you want to. But once you figure out the geometry, from now on, you have to redraw it to reflect that geometry. Does that make sense? All right? And again, the reason why the shapes happen, folks, is because of the electrons, that valence shell electron pair repulsion. The electrons are pushing each other away because they have like charges. They want to be in the lowest energy state possible. The further away those negatives are from each other, the less energy the whole structure is going to have, the less strain on your molecule. Easy? It's easy if you know your shapes. I've told you guys since last week, make flashcards. On one side, write the name. On the other side, put the formula and draw the shape that you see in that chart. Then look over them over and over again. It's going to make it easy for you. Questions? I want you guys to do sulfur difluoride. Go through the whole process. Draw the structure first, then do your best to take a shot at identifying the geometry. Our formula here is going to be SF2, 6 plus 14. We have 20 total electrons to work with. When we go through new, we have S, we've got F. Connect the dots, or connect the elements there with a line. There, that takes out 4. We've got 16 left to work with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so I've still got 4 more. Now I can go back to my central atom, guys. We can put electron pairs on the central atom. We just wait until the last ones is the last resort. If we have some left over, we have 4, which is how many sulfur needs. There's what our structure might look like. It's our first one. Now we're going to figure out the geometry of it. So we're going to put it in that ABE form. Again, you don't have to write over. I encourage you guys to write over those. So central atom gets the letter what? A. So our whole shape, guys, is in relation to that center atom. That's A. Satellite atoms get the letter B. Now, if we have lone pairs, the last one we didn't have lone pairs. Do we have lone pairs on the central atom now? Yes, we do. What letter do they get? E. Okay? So now when we look at our formula, AB2, E2. Okay? There's our formula. AB2E2. When we take a look at it, it's not linear. It's not this first bend because that's AB2E. It's not trigonoplanar. It's not tetrahedral. It's not trigonopyramidal. It's our second bent. And that should make sense with what our structure looks like. We actually drew it bent, or I did here, just because the order that I usually fill in, it makes it bent. Now let's talk about why. Why is it bent here, guys? Well, the real reason that it is a bent molecule, I'm going to go back to my original one and mark it up some, is these lone pairs. Guys, lone pairs have a lot of energy here. So if you notice on your sheet that has the picture, I don't think, no, mine does not, but take a look, guys, at the pictures that you have. All right? Those lone pairs have a lot of energy. Right? They're not being shared. They're just there. They are the piece that really dictate however the rest of the molecule is going to look. That valence shell electron pair repulsion. If you have electron pairs, guys, on your central atom, they are going to push everything else away, which causes the shape that you see. They are pushing these away to make the other two elements bent instead of that linear line. All right. So you'll notice if we look at trigonal, I'm going to show you some shapes here in just a second. But if you look at all of those, like the trigonal pyramidal, it's got a lone pair on there. It's going to push everything else down. What makes it difficult is when you have to memorize them. You don't have that to look at, like on your quiz tomorrow and your test next Tuesday. All right. There's no questions. Let's do this last one here together. Example number 3. SF6. How many total electrons do I have to work with? 6 times 7 is? So a total of 48 valence electrons. This is a lot. This is the most we've ever had. What's my central atom going to be? S. I'm going to put my fluorines all around it. I've got 6 of them. I'm going to connect them all. Well, that's 6 bonds, so I'm going to subtract out 12 electrons. Oh, look, I've got 32. I'm sorry, can't do math. 36 left over. Where are all those 36 going to go? All the Fs are going to get those. So far, it's the same process. But what do you guys notice as I'm putting all these dots around it? What's different about this structure? Sulfur has more than 8 valence electrons, guys. Sulfur has how many? 2, 4, 6, 8, 10, 12. Holy cow, that's a lot more. Is that okay, do you think? Apparently it is, right? It is okay here, guys. Like I've said the other day, there are always some exceptions to the rule. Sulfur is one of those. Phosphorus is one of those. Boron is one of those where they will have exceptions. Now, we're not going to see a structure like this. But for the sake of practice, let's go through our same process. A is my central atom. B are all of my satellite atoms. So what's my structure going to be? Right, because we have A, B, 6. This is actually an octahedral structure. Very rare. We don't see them a lot. All right. Sometimes, remember sulfur hexafluoride. Does anybody remember? I showed you guys a video of what sulfur hexafluoride will do to you. Jimmy Fallon video. Yeah, it did something to their voice.
Oh, it makes it really deep, right?
Right. Helium makes it go high. Sulfur hexafluoride, this stuff, makes it go really low.
We should do that.
If I want to get some. I can't. I don't know how to get sulfur hexafluoride. I've always wanted to try it. I don't have a guy for this. I'm sure you do.
It's like you can get the
You can. Sulfur hexafluoride you can too. It's just really expensive. All right, guys. What I want you to do for some practice with VSEPR, you're going to go back to page 9, which is your homework last week. All 14 structures that you already should have written out. You're going to go through and do that. Ionic will never use VSEPR. All right, there's no molecular geometries there, guys. Molecular is the key word within that. Molecular means covalent. So if you have an ionic bond, it will not use valence shell electron pair repulsion. Because there's not going to be any electron pairs, really, because you have what holding ionic bonds together? What will hold those together that makes them stronger than covalent bonds? Think about it. Ionic. Ions which have a charge, so that electrostatic attraction between the charges is what holds them together. So when we draw an ionic structure, we've done this. We did this back in Unit 4. It's a review. It's been a while, which is why I wanted to do one together. All right. We have Ki, potassium iodide. We know it's ionic. We got a metal and a nonmetal. So we're going to start to draw those out. I've got K and I've got I. Draw their Lewis dot diagrams for those. K has how many valence electrons? 1. Iodine has 7. Now, with an ionic bond, guys, what do we show between the two? An arrow, right? Because what's happening with the electrons? Not a share. There's a transfer, guys, that give and take. Who's going to transfer their electrons to the other one? Yeah, potassium is going to transfer it over. So then your final structure will look at this. You don't have to, guys, in this worksheet for homework, draw the arrows. Okay? All I'm looking for is the final one within it. So K is going to have brackets around it with a +1 charge. Iodine is going to have all of its dots, like we did with our notes last week when you guys had to go through and you're like, I don't know how to draw ions. This is what an ionic bond would look like. So if you have an ionic structure, this is what I'm looking for. It'll be this way on your quiz tomorrow if I give you one, as well as your test next Tuesday.